So here we begin with section 7.7, which deals with atomic orbitals. I want to point out that table 7.2 on page 300 of your book shows the relation between quantum numbers and the atomic orbitals. When studying atomic orbitals, a common question that comes up is, okay, so what are the shapes of orbitals? Well, strictly speaking, an orbital does not have a well-defined shape because the wave function characterizing the orbital extends from the nucleus to infinity. And in that sense, it's pretty difficult to say what an orbital looks like, but it's really convenient for us humans to set orbitals as having specific shapes. So the first atomic orbital is the s orbital, and you can see that it's basically a sphere. So if you remember from the last video where I said that the s orbital can only have one orientation, you can see it here. It's because it's a sphere. You can only orient a sphere one way. So all s orbitals are spherical in shape but differ in size, which of course increases as the principal quantum number increases. And you can tell on the right where I've shown you the little mini periodic table, hydrogen has a 1s orbital, then you go down to lithium that has a 2s orbital, so on and so forth. The p orbitals corresponds to L equals 1, and this has a dumbbell shape. The fact that the angular momentum quantum number L is equal to 1 means that it can have 3 different orientations, because remember, m sub L depends on L, and since L is equal to 1, then m sub L is -1, 0, and 1, and that's because it can have 3 different orientations. The p orbital begins at n equals 2. It's the green on the right hand side of the periodic table. So for example, if I wanted to find out what the electronic configuration of boron is, I would have to go through all of the elements before boron. So I would have to say 1s2 because I have to account for hydrogen and helium, and then go to the next row. 2s2, that accounts for lithium and beryllium, and then I say 2p1. If you count up all the electrons or the superscripts, you'll see that you have 5 electrons, which is equal to how many electrons boron has. Alright, let's move on. Here we have the d orbitals. When L equals 2, the angular momentum number equals 2, there are 5 values of m sub L, magnetic quantum number, which of course correspond to 5 different orientations. So basically it's sort of like 2 dumbbells put together. The lowest value of a d orbital is n equals 3. If you look in row 4, which starts with potassium, and you look at the d orbitals, which is the blue, you notice that they -1 when you go to the d orbitals. The d orbitals are basically the transition metals, and this has to do with energy. The reason these orbitals have these letters and numbers and everything, it's because of the energy level that they're in. So for right now, just take what I'm saying and put it in the back of your head. I know it does not make sense to you right now that you see a 4s and then all of a sudden it goes to 3d, but it's all because of energy. There is lower energy in the transition metals, so those energy levels occupy first. As far as electrons occupy those energy states first than they would a 4s level. So that's the background information for that. It's important to note that if you're in a particular orbital, like for example, if you're in a 3d orbital or a 2s orbital or a 5p orbital, if you're in one orbital, all atoms have identical energy in that particular orbital. Orbitals having higher energy than d orbitals basically are labeled F, G, and so on. The F orbitals are important in accounting for the behavior of elements with atomic numbers greater than 57, but their shapes are really hard to represent, so we're not gonna even look at those. So all you have to really worry about is naming the S, the P's, the D's, and the F's. Alright, let's do some problems. This is number 7.57 in the back of your chapter. It reads, list the values of n, L, and m sub L for orbitals in the following subshells: 3s, 2p, and 5d. 3 different problems. So let's do the first one, 3s. When you see a problem like this, you have to ask yourself, what does the number 3 mean? 3 means what row it sits in. That's the principal quantum number. So n would be equal to 3. The letter s designates the type of orbital it is. We're dealing here with an s orbital. So the s orbital can really only have one orientation. So L would be equal to S, and then M sub L depends on L. How many different orientations it has? Well, S is a sphere, so it only has one orientation. So that means that your M sub L would also be 0. So you have N equals 3, L equals 0, and ML equals 0. All right, let's do the second one. 2p. 2 signifies principal quantum number, so that's N is equal to 2. The L would be the letter, okay? And a p orbital corresponds to number 1. And because we are dealing with a p orbital, that means that we have 3 different orientations. So your M sub L would be -1, 0, and 1. Those are your 3 different orientations. So your N is equal to 2, your L is equal to 1, and your M sub L is equal to -1, 0, or 1. The last one is 5D. So your N here would be 5. Your L corresponds to D, and D means that L would be 2. So that means that your M sub L would be -2, -1, 0, 1, and 2. This is a D subshell, so they have 5 different orientations. That's why you have 5 different numbers for M sub L. All right, let's move on. This is practice exercise 7.8, and it reads, what is the total number of orbitals associated with the principal quantum number N equals 4? So this is more of a general question. Okay, so how many total number of orbitals can I have if I have N equals 4? Well, I'm going to do it the long way, and then after I'm going to show you a little trick that we use to find this very quickly. To do this problem the long way, which is good if you wanted to check, N is equal to 4. So what does that mean? L. L is defined by N. So L can be from 0 all the way to N minus 1. That means that L can be 0, 1, 2, or 3. Now we have to find M sub L, because that's the orbital. That's the number of orbitals there are. So M sub L depends on L, right? And remember, whatever L is, then you can have negative L to positive L. So you have to take each of those subshells individually. So you take, okay, so for L equals 0, M sub L can only be 0. For L equals 1, M sub L can only be -1, 0, or 1. For L equals 2, M sub L can be -2, -1, 0, 1, and 2. And for the last one, L equals 3, M sub L can be -3, -2, -1, 0, 1, 2, and 3. If you count all those orbitals, you have 16 orbitals. So for a principal number, N equals 4, you can have a total possible of 16 orbitals associated with that number, with that principal quantum number. Now, the fast way to do this is the total number of orbitals for a given value of N is equal to N squared. So all you would have to do is square 4. So 4 squared is 16. And that actually matches up with what we got, which is 16 total orbitals. Okay, let's move on. Let's go back to Schrodinger's wave equation, and here are the quantum numbers that we're very familiar with now. N, L, M sub L, and M sub S. M sub S we really haven't talked about because you'll see it's the easiest one and we don't really even need to worry about it, but we will a little bit later. So Pauli exclusion principle. This is a principle which basically states that no 2 electrons in an atom can have the same 4 quantum numbers. Remember that address that I talked about? Or, every person in a stadium has a particular seat. Only one person can sit in that seat for that game. So think about it like that. But this exclusion principle is a definition that you are required to remember. It states, again, that no 2 electrons in an atom can have the same 4 quantum numbers because everybody has their own address. All right, let's move on. Now that we have a little bit of a understanding of the shapes and sizes of atomic orbitals, we can start talking about relative energies and how to look at those energy levels and how they affect the actual arrangement of electrons in atoms. According to Bohr's theory, which we didn't really go over, he stated that the energy of an electron in a hydrogen atom is determined solely by its principal quantum number. So what does that mean? That means that 1s is less than 2s, but 2s is the same energy level as 2p because it has the same principal quantum number, and 3s would be this equal energy as 3p as well as 3d, and that's true, but only for a single electron atom. So really it limited to hydrogen. So you can see here that 1s is all the way super low energy, but then as you increase the rows 2, 3, and 4, you get increasing energy. And this seems very simple, but there's only one atom in the periodic table that has 1 electron. So how do we describe the energy levels for a multi-electron atom? That's what we're going to talk about next. So here's a picture of what the energy diagram looks like for orbitals in a multi-electron atom. The energy doesn't only depend on the principal quantum number, it depends on the angular momentum quantum number as well. So N and L. So I want you to notice that even if you're in the same row, like 2s and 2p, that's the same principal quantum number, but you can see that the s orbital is a little bit less energy than the p orbital. And the same thing goes for the 3s and the 3p. I want you to note though that the 3d energy level is very close to the 4s energy level. And that's why you'll see later on when we go to the transition metals to find the electronic configurations, we go from the 4s to the 3d before we go back to the 4p. And you'll see that each orbital, so basically each little line, can hold 2 electrons. And remember, that's what we talked about. That's the m sub s, the spin quantum number. So each of those little lines can hold 2 electrons, one spin up, one spin down. But like I said, it turns out that the total energy of an atom is lower when the 4s subshell is filled before a 3d subshell. And that'll make a little bit more sense as we go on. A couple more of bookkeeping items. So another principle that you guys should be aware of is the Aufbau principle. And basically it states that the electrons fill up the lowest energy orbitals first. Okay, so that's the way that they fill up. So the 1s will be filled up, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d. All right, so it just keeps going on and on like that. So electrons are not going to fill up naturally a 4d before they fill up a 1s orbital. Let's talk about another bookkeeping item. This rule, the Hund's rule, states that the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins. So the way that you would fill these electron orbitals up is, of course, 1s, and then you have to do the spin down. One spin up, spin down, and then you go to 2s. 1 electron up, 1 electron down. But then you have something like 2p, which has those 3 different orientations. So the way that would fill up is an electron spin up, and then an electron in the next orbital spin up, and an electron in the next orbital spin up, and then you go back to the beginning, the first orbital, and do spin down, okay? And then you fill them up like that. So again, the most stable arrangement of electrons in these orbitals within the subshells is the one with the greatest number of parallel spins. All right, let's start talking about electronic configuration. So this is it, electronic configuration. This shows us how the electrons are distributed among various atomic orbitals in an atom. I've kind of alluded to this before in the earlier videos, but as you already know, the principal quantum number N, that's the number, the angular momentum quantum number L, that's the letter, and then the number of electrons in that particular orbital. That's the little subscript that you see on the top there. So for hydrogen, like I said before, would be 1 because it's in row 1, S because it's a sphere and the angular momentum is equal to 0. And then how many electrons does hydrogen have? Well, it has 1, so 1s1. How about if we did carbon? Remember what I told you, you have to go through all of the atoms before you get to the one that you're dealing with. So carbon, you would have to go through 1s1, which is hydrogen, and then 1s2, which is helium. But you can combine those because remember, those little lines, those little orbitals can hold up to 2 electrons. So you can go ahead and say 1s2, which you will know that you've gone through row 1 of the periodic table. All right, so let's keep going. So for carbon, it would be 1s2, then 2s2, then you would go to 2p1 and 2p2. You don't have to write 2p1 and 2p2. All you would have to write is 2p2. So the electronic configuration for carbon would be 1s2, 2s2, 2p2. How about phosphorus? Well, phosphorus has 15 electrons. So we have to somehow get to 15. All right, so let's do this. 1s2, 2s2, and then you have the 2 p's, but you can fit up to, remember, p has 3 different orientations. So you have 3 little lines, which can hold up to 6 electrons. So you would do 2p6, that takes care of everybody between boron and neon. And then you go down to the third row, 3s2, and then you have to go to phosphorus, which is 3p3. And if you count all those subscripts up, you'll see that you get 15 electrons. I'm going to do one more video, but the video is just going to go over problems that that deal with these type of electronic configurations and quantum numbers. So I'm not going to test you on that one, but I would suggest that you guys look at it because it's going to do all problems that you're going to be dealing with for this chapter. And of course, read the last sections, which talk about the general rules for assigning electrons to atomic orbitals. I do want to point out that in page 311 of your book, you do have the ground state electron configurations of all the elements, so you can look at them and notice that they've used a shorthand, and I will teach you that shorthand in the next video, which you're not responsible for, but we're going to talk about a lot of problems. All right, see you later.